I'd like to introduce Vasu Sharma. Vasu is interested in the irrigation water management, water and nitrogen fertilizer interactions, crop evapotranspiration, and variable irrigation and cover crop research work. Vasu's appointment is quite unique in the fact that it's funded by Clean Water Legacy, and she's been extremely successful in building funding partnerships shared by AFREC, Minnesota irrigators, some of our local soil and water districts, and clean water. So please welcome Vasu. Yeah, you guys that too for here.
Okay. Yeah, thanks, Bruce. So my name is Vasu Sharma. I'm the irrigation specialist in soil, water, and climate department at the University of Minnesota. And today I'll be talking about the integration of irrigation and nitrogen management for optimum corn production. So AKA interactions of irrigation and nitrogen. I will be showing you some data. So all the studies that I'm talking about today are ongoing because everything started in 2020. So I'll be showing you some data and some updates on what we are trying to do. So as you know, two major inputs to corn production, the two important things, water and nitrogen, without which I think the crop production won't be as we have today. So these are the two important components that are also interdependent. So they are interrelated. And we know that when we increase irrigation and nitrogen input, it maximizes corn yield up to an optimum level. And that level can vary substantially with where you are growing that crop, the region, climate and soil characteristics, management practices, hybrid, and other factors. So that's where it's very important to look at how these two variables interact with each other in different climates and different soils and regions. So with the water scarcity issues that we are looking in Minnesota as well now, and water quality issues, there is interest in deficit irrigation or limited irrigation management. So with that, the nitrogen recommendations, they needs to be adjusted correspondingly based on how much water you're applying to your crop. And knowledge about plant response to nitrogen fertilizer and irrigation water is very important in developing these best management practices that we use if we are using some different irrigation management strategies like deficit irrigation or limited irrigation in the near future. So that's where this research comes in, because we don't have that information here for our state, those basic data for developing these BMPs, where we are looking at interaction of irrigation, water, and nitrogen. So just some background about irrigation. If you're not familiar, there are around 600,000 acres of crop irrigation, and 93% of that irrigation happens through sprinkler irrigation, so overhead irrigation, center pivot, or linear moves. Mostly the irrigation happens in glacial outwash sands that dominates the central Minnesota. So here the map on the right shows you the active agricultural irrigation permits data from DNR. And the blue dots are active irrigation permits. And you see most of these are either in Dakota County area, concentration is here, or the sandy outwash sands in central Minnesota. And the main crops that are grown here are corn, mostly 48% up to 50%, soybeans, dry beans, potatoes, and some other specialty crops. The water that is used for irrigation is from the groundwater, so 93% of irrigation water applied to these acres comes from groundwater from on-farm wells. And we have seen a substantial increase. So this is the data from USDA census. From 2002 to 2017 in Minnesota, there has been 34% increase in irrigated acres. So it's a huge increase. In terms of how much we are irrigating, it's only around 3.8 to 4% of total croplands that we are irrigating. But in terms of water use, irrigation is using lots of water, fresh water. And the major issue, as I talked about water quantity that's being seen in different regions in the state, the major one is the nitrate leaching or water quality issue. So this is the map on the left that shows you nitrate as nitrogen in drinking water wells from Department of Health in 2014. The red dots indicated where the nitrate level is more than 10 parts per million, and that corresponds to agricultural irrigation permits as well, because it's not just the irrigation, agricultural irrigation, but mostly the soils where we are irrigating. So most of the sandy soils region in the central Minnesota have higher nitrates in drinking water. And one reason could be the agricultural irrigation. So the project that I'm going to talk to you about is looking at the coupling effect of irrigation and nitrogen rate on corn yield, water and nitrogen use efficiencies, and water quality and quantity. And the main objective is to evaluate how these different irrigation and nitrogen rate interact with each other and has an effect on any effect. We don't know yet if there is or there is not. So we are looking at the effects on corn yield, nitrate nitrogen leaching, crop ET, crop water productivity and efficiencies, and then develop best management practices that optimize corn production and groundwater usage and minimize nitrate leaching. There is a third component to this study where we are looking at UAV remote sensing data and trying to develop some UAV remote sensing non-destructive in-season corn water and nitrogen status diagnosis method. So how we can use remotely sensed data for irrigation and water management in irrigation and nitrogen management in season. So 5 corn growing seasons. If you have been in my presentations previously, I talked about this study and I said 3 growing seasons. So this was the last year. Initially, we started in 2020 and we thought 3 years of data would be sufficient to provide some, basic response curves, how corn responds to irrigation and nitrogen. But with last 2 years, which were exceptionally dry years, we thought it's good to have more data. So we extended this study 2 more years. So this growing season and next growing season, so 5 growing seasons. The study is being conducted at 2 research sites, Sand Plain Research Farm in Becker, Minnesota, and Rochelle Research Farm in Westport. Both soils are in central sandy outwash, coarse textured soils and vulnerable groundwater areas where leaching is a huge issue. The experimental design is, so this is our Becker site. We have 4 irrigation treatments. So full irrigation treatment, 100%, which means we are filling back our soil profile to close to field capacity, leaving some room for precipitation every time there is 40 to 50% depletion. Then 75% of that full irrigation, 50% and no irrigation. And then 6 nitrogen rates starting from 0 pounds to 350 pounds of nitrogen per acre with 70 pounds increments. So total, there are 24 treatments that are replicated 4 times. So if you look at this figure, there are 96 plots. So the big one, the red one, are the replications. Within each replication, we have white boxes, which are irrigation treatments, and within each irrigation treatment, we have 6 nitrogen rates. When I talked about 100% irrigation, mostly people ask question, what is that 100% irrigation? So I just put this slide here to show you different levels of soil moisture. So our goal with 100% irrigation is whenever our soil moisture is close to this irrigation trigger, which is mostly 45 to 50% in corn, the depletion is 45 to 50% of this plant available water, we irrigate and we bring that soil moisture back to very close to field capacity. So filling that the range, optimum range for 100%. And then once we know that 100% amount, we cut that to 75 and 50% for other rates. We measure for a nitrate leaching component, we measure water samples at 4 feet depth. So we installed 192 suction cup lysimeters at each site. Just a little explanation of what this lysimeter is. So there's a porous cup at the bottom of this PVC tube, if you see this, and this porous cup is installed at 4 feet soil depth, which is below the corn root zone. And at all times, this PVC tube, which has a stopper on top, is under vacuum, under tension. So every week, the water is collected in this PVC pipe, and we come and we collect the water sample and send it to lab, and then put that PVC pipe, the lysimeter back under suction so that it can collect next week's data. So that's how we collect that water sample from 192 suction cup lysimeters every week, which are permanently installed at both sites. So approximately 10,000 water samples per year that we collect from this study. And then from each of our treatment, we also measure soil moisture so that we can schedule irrigations, and then later on also use water balance method for calculating drainage and evapotranspiration. So we are using a neutron probe, which is kind of a standard method of measuring volumetric water content at 72 locations at each site. And then during the growing season, we collect plant samples and soil samples to look at how, to look at the nitrogen dynamics, how with different irrigation rates and different nitrogen rates, nitrogen uptake changes. And for our third objective, which is remote sensing UAV, we are measuring some proximal and remote sensing data using different sensors, which I'm not going to show a lot of data about it, but just to give you an update that this is the third component of the study where we are looking at some remotely sensed data and see how we can use that and make relations with our ground truth data for our in-season water and nitrogen management. So looking at, so I have data for complete data for 2020 and 2021. So last year, 2022, we collected data, but I don't have all the results yet. So I'll be sharing some data with you today here. So the two sites, the left graph shows you the precipitation at Westport and the right one at Becker. And we see the 3 years were completely different in terms of precipitation. In 2020 at Westport, we got around 18 inches, which was close to long-term average of 20.5 inches, the growing season average. In 2021, which was a dry year, but if you look at the cumulative precipitation at Westport, we got around 20 inches, which was actually very close to long-term average, but it was a dry year. So if you look at the trend, this 2021 data, which is orange line, for most of the season until mid-August, we did not get much rain. And that heavy rain at the end of August, early September brought that cumulative precipitation to even more than 2020. And then 2022, overall, we got the cumulative precipitation was 11 inches, which was way below than long-term average. But if you look at the rainfall during the growing season, we did get good rains when we needed them in 2022 at Westport. Becker had somewhat different pattern of precipitation. In 2020, we got 16 inches, so close to long-term average out of these three, then 12 inches in 2021. So we did not get those heavy rains that we got at Westport in 2021 in Becker. And then 2022, 13 inches of rain. So at Becker, 2021 wasn't very different from 2022. I'm showing you this data because most of our results are dictated by what happened in terms of precipitation, how we irrigated and how the yield and other variables came out. So this is the irrigation following the trend of precipitation in the first year, the 100%. So overall, Westport got lower irrigation than Becker because we got more rains at Westport than at Becker. 2021 at both locations had the highest irrigation because we got least water and precipitation during the growing season. And then 2022 got a little bit lower than 2021, but still, in fact, lower than 2020 in Becker. And that's based on our in-season soil moisture measurements. So soil moisture was good. Even the last year was a dry year, but the timely rain happened at Becker and Westport. So almost 3.2 inches in 2020, 8 inches and 4 inches at Westport, and 100% irrigation plots, and a little bit more at Becker, 7, 13, and 6 inches. So 2020 and 2022 had almost same amount of irrigation at both sites. So how the yield respond to nitrogen and irrigation. So at Westport, this is 3 years of data. So the x-axis shows you the nitrogen in pounds per acre that we applied. And then one thing I forgot, nitrogen was applied in 2 splits at V2 and at V8. So the first graph is 2020 corn yield on y-axis. In 2020, which was the precipitation was very close to long-term average, we did not see a significant difference between yield in any of our irrigation treatments. So all the 3 lines, so the 4 lines here are the 4 irrigation treatments. They are on top of each other. So not a very big difference between yield at any nitrogen rate in 2020. However, in 2021, which was a dry year, we saw significant reduction in grain yield at rain-fed, which are these yellow triangles. But if you look at the 3 irrigation treatments, the difference between the yield, even in 2021, which was a dry year, wasn't that significant in Westport. And one reason could be those heavy rains, which weren't very late, which were like mid of August, which actually added up to the yield, and the yield wasn't that different between the irrigation treatments in Westport. 2022, again, the rain-fed yield was significantly lower. If we look at the 3 lines here, the irrigation treatments, the 50% had lower yield than 75% and 100%, whereas 100% and 75% weren't that different. So almost same yield in 175% irrigation at Westport. The irrigation response, the yield response to irrigation. So here on these three years, the x-axis is irrigation, y-axis is yield. In the first year, as expected, because there was good rain, the irrigation was very less. The response of grain yield to irrigation is almost, there's no response to straight lines. But when we have dry years, we did see a significant response of grain yield to irrigation, and specifically at higher nitrogen rates. So 350 pounds, 280 and 210 pounds of nitrogen per acre, we got a very significant grain yield response to irrigation. So as we increase the irrigation, the grain yield increases, and then there is that flat line. So it plateaus at some higher irrigation rates. Similar graphs for Becker, but slightly different results that we found at Westport. And the main reason, as I mentioned, was the precipitation. The first year, 2020, very close. The precipitation was very close to long-term average. We did not see any significant differences between irrigation treatments. 2021, almost no yield in rain-fed plots, 0. And the big difference between irrigation treatments as well, which we did not see at Westport. So 50% irrigation was significantly lower than 75% and 75% than 100%. So 100% got maximum yield. Similar results in 2022 again. The rain-fed was the lowest, and then as we increased the water, the yield increased at Becker. Yield response to irrigation. So grain yield in first year 2020, which was close to average, even it was not above average, it was a little bit lower than long-term average. We still see no response to irrigation. So grain yield, as you increase the irrigation, there's no increase in grain, your very slight increase in grain yield at all levels of nitrogen. In 2021 and 2022, we did see a significant increase in grain yield when we increased the irrigation. So lower irrigations had lower yield at all levels of nitrogen. The trend is more significant for higher rates of nitrogen than for lower. And then we also looked at how nitrogen application and irrigation impact nitrogen uptake. So the left 2 graphs are 2020 data at Westport. So the top one is R6 nitrogen uptake, only the green part, and then the grain nitrogen uptake. We separated these two. And in 2020, we did not see any difference at any rate of nitrogen in grain nitrogen uptake or even in R6 nitrogen uptake. Slight differences occur at higher rates of nitrogen, where we saw a decrease in R6N uptake at 100% than other treatments. In 2021, which was a dry year, no difference in R6N uptake, but grain nitrogen uptake was significantly different. We did see lower grain nitrogen in rain-fed plots. However, our irrigation treatments, all 3 had almost same grain nitrogen. So no difference even in 2021 at Westport. Becker had different stories. So 2020 was similar as Westport, no differences either in R6 nitrogen uptake or grain nitrogen uptake. But 2021, which was extremely dry at Becker, we did see a significant increase in R6N uptake in rain-fed plot, because most of that nitrogen was accumulated in the green part rather than the grain. So grain had significantly lower nitrogen content in in rain-fed plots. And we look at these three lines, which are three irrigation treatments. 50% irrigation had lower grain nitrogen than uptake than 75% and 100%. And these results are very much related to how the grain yield data that I showed you in the previous slide. So similar pattern of grain nitrogen uptake as the yield. And then, as I said, we have nitrate leaching data as well. So we collect water samples, and for each of our treatment, we looked at how the nitrate leaching, what happened to nitrate leaching. So at Becker, the top graph, so I just plotted that nitrate leaching data with irrigation, wanted to see what happens when we increase the irrigation to nitrate leaching. So Becker, we see that with increase in irrigation, actually nitrate leaching decreased at Becker, and then and I haven't done a lot of analysis to this. This is just plotting of data, but this looks very promising to me from first 2 years. So this is 2020 and 2021 data. We see that with decrease in irrigation, with increase in irrigation, the nitrate leaching decreased, and after some point of irrigation, it again starts increasing. We did not see this trend at Westport. We did a straight increase at in nitrate leaching with increase in irrigation. And the three lines here indicate, so for sake of simplicity, I divided our nitrogen rates to low, medium, and high. So the high one is average of 280 and 350 pounds of nitrogen per acre. Medium is 140 and 210. And then the low one is 0 to 70 pounds of nitrogen. So three lines indicate different rates of nitrogen. So there is sure a trend in leaching with nitrate application. So as you increase the nitrate application, the leaching increases, but as you increase the irrigation rate at Becker, there's this decreasing and then increasing trend, and at Westport, there is straight increasing trend at all rates of nitrogen. And then I thought, let's plot the same thing with plant and uptake at R6, so both grain and R6, and see if that follows the similar trend as nitrate leaching. So if there is more nitrate leaching happening with increase in irrigation, that means there should be less grain nitrogen uptake, but we did not see that at Westport. We did see the similar trend at Becker. So as the nitrate leaching decreases with increase in irrigation, the grain nitrogen, the plant nitrogen uptake increases at Becker, and then there is this critical point where it starts decreasing again. But at Westport, we did not see that trend. We see an increase in plant nitrogen uptake with increase in irrigation, even though there was increase in nitrate leaching as well with increase in irrigation. I hope this makes sense. And then because one of the goals is to develop best management practices and see if our EONR changes with irrigation, with increase or decrease in irrigation. So we looked at the economic optimum nitrogen rate for each of our treatment, and then I tried to plot it with irrigation. What happens to EONR when we increase irrigation? So the red dots are Westport, the yellow triangles are Becker, and we did see the same trend at both sites, that with increase in irrigation, the economic optimum nitrogen rate increases. It has that that maximum level, and then it decreases at higher irrigation rates. So this is also very interesting. And as I said, this is just 2 years of data, and we are doing this study for 5 years. So maybe with change in weather, we have 2 dry years. I hope that next 2 years are okay years, not too much rain or too dry, so then we can find or complete this response curve. For our remote sensing data, we do collect temperature, canopy temperature, thermal images, and we do get some promising results. So this is just a snip of what we found in the first year. So the T air minus T canopy, we did see a response of irrigation to this parameter. As we increase the irrigation, the difference between canopy temperature and air temperature increases. So this signature can be used for, and some other thermal data can be used for in-season water management, and similar for nitrogen. So we looked at the normalized difference red edge index and see that that has a trend with nitrogen rates. As we increase the nitrogen rate, the NDRE increases. So this can be used for in-season nitrogen management. As I said, we extended this study for 2 more years, and then we did change. We had a slight change in the treatment plan. I showed you many graphs. We thought that it would be good to include 125% of full irrigation. So we didn't have that very, very high rate of irrigation to look at how more than your soil can hold if you put that much of water. What happens to nitrate leaching, crop yield, and other parameters that I looked at. So we added 125 and we replaced 75 and 50% with 65%. So for the next 2 years, we'll be using this treatment plan. Everything else remains same. So key findings so far, for sure, we did see an impact of irrigation on crop yield and on nitrate leaching. And we think that reduced irrigation management in humid climates has a potential in decreasing the irrigation amount and reducing nitrate leaching losses, but we need more data. In the average precipitation year like 2020, we see 31% reduction in irrigation, decreased 43% nitrate leaching, with 6.5% yield reduction at Becker. So there was yield reduction at Becker, but there was also decrease in nitrate leaching. At Westport, we did see an increase in yield with reduction of water. So 43% reduction in irrigation resulted in 55% reduction in nitrate leaching, with 4% increase in yield in 2020, which was average precipitation year. And we did see differences in site. Westport has different results than Becker, and that's mainly because of the precipitation pattern. So I'm just going to introduce one more study here, which we started last year. Dr. Yushin Mir is the co-PI on this project. We are looking at how we can use the data that we developed in this research that I just showed you, some of that data in looking at how we can use that data for precision irrigation and nitrogen management. So in season, using remote sensing data or UAV data, how we can use that data for in-season water and nitrogen management. So the idea is to quantify and evaluate the impact of both variable rate irrigation and variable rate nitrogen in comparison to conventional methods, and develop some in-season diagnosis method and evaluate the economics of VRI. So this is the study that we started at Becker Research Farm. This is a 25-acre field, and we divided this. So the pie shapes here are the irrigation treatments. The black ones are uniform rate irrigation, and these are the variable rate irrigation. And then our nitrogen treatments are applied in split. So we assume that our farmers' nitrogen or normal rate in these soils are around 220 pounds of nitrogen per acre. And then we divided that. So we have 4 treatments. What we did is 20% of farmers' nitrogen rate at planting, and then the rest of it, the variable rate nitrogen, that will be based on the remote sensing data in the second split. And then 30% FNR plus VRN, 40% FNR VRN. And our last treatment is we just divided this 220 pounds into 2 splits. So 50% at planting and then 50% at V8. Our variable rate nitrogen, as I said, is based on our NDVI and NDRE data from the PlanetScope images. So the white lines here on the graph are the management zones. So we collected some soil texture data, EC data, and based on these 2, and elevation data, and based on these 3 data sets, we developed these management zones. And for the first year, which was last year, we used these management zones as static. So we know zone 1, always zone 1 will get a particular amount of irrigation, and then other zones will get the reduced amount of irrigation. For our first year, that approach didn't work very well. So we got a little bit lower yields under variable rate irrigation than under uniform rate irrigation. One reason could be the dry year at Becker. And then the second reason could be that our approach wasn't that good because we were just using fixed management zones for the whole season and based our irrigation scheduling based on the soil moisture sensors. So we had 27 soil moisture sensors in this field and the lysimeters where we are collecting the water samples each week. I don't have any results to show you yet, but just an update that this is an ongoing study and we'll be continuing this study for 3 years. And this year, learning from the first year that we might not be using best approach for variable rate irrigation. So we'll be using some thermal, UAV thermal image data for getting to crop water stress index and look at how we can use that data for in-season water management. So rather than using static management zones, we use dynamic management zones for irrigation as well. Some extension and outreach efforts. So we do many programs focused on irrigation and nitrogen management. The first one, which I want to highlight today, is Minnesota Irrigators Program. The second one is NRCS Regional Conservation Partnership Program, which we call RCPP. And then we also do many irrigation and nutrient management field days that we publicize through our Minnesota Crop News. So if you can subscribe to that, that would be great. So the Minnesota Irrigators Program, this is the second year of this program. We did last year in St.Cloud 2-day event that provided intensive training on irrigation practices that can conserve water and limit the impact of ground and surface water quality. And this year, from last year's reviews and feedback, we extended this for 3 days in Dakota County. So March 1st, March 8th, and March 15th, we'll be conducting this program where we'll be talking about a range of topics, starting from basics, irrigation scheduling methods, soil moisture sensors, to variable rate irrigation, precision irrigation, nitrogen management, drip irrigation, remote sensing, ET. So a range of topics that will be covered. One incentive to this program is that Minnesota Agriculture Water Quality certified growers can use irrigation endorsement if they will get irrigation endorsement if they attend this program for 3 days. And there are also soil water management CEUs that are being offered. So if you haven't registered and if you're interested and if you know someone who will be interested, please share this with them. The second program that I want to highlight is RCPP. Yaba is here and I'm using Yaba's slides here to just give you an update on this program. So this was the funding that MDA got from NRCS, around $3.5 million that are being used for implementation, irrigation conservation implementation purposes. The first round of funding was from May 5 to June 15. So applications were taken in from May 5th to June 15th, 2022, and 12 contracts were funded, which were located in Becker, East Otter Tail, Dakota, Kandiyohi, Sherburne, Stearns, and Vadina SWCD service areas, and around $685,000 of financial assistance was given to the growers. The second round of funding, so the practices that are covered under these are variable rate irrigation, starting from BRI, advanced irrigation water management using soil moisture sensors, cover crops, to retrofitting your fertigation on your irrigation system. The second round closed on December 16th, 2022. And right now the NRCS is processing the application. So there was around $1.7 million that was available for the second round. So yeah, we may spend all of that money in the second round. Just an update that this is an ongoing program. At the end, I want to acknowledge all the funding agencies, my co-PIs, graduate students who are working very hard on collecting data, our field crew, and other farmers and industry collaborators. And that would be all. Thank you. I can take any questions. Oh, so nitrate leaching, I think I showed in one of the slides, was measured using suction cup lysimeters. So we installed around 2 suction cup lysimeters in each plot at 4 feet depth, and then collect that water sample that's going below the root zone every week, and then send it to lab for nitrate analysis. Why do you see such a difference in nitrate leaching between 2 locations? One reason is there could be two reasons. One reason, main reason, which I think is the precipitation. So I showed the precipitation graph at the beginning. We did see a huge difference in how in the pattern of precipitation. So at Westport, we did get very timely precipitation. Even in wet year at the end of the season, around 15 August and onwards, we got very heavy rains that impacted nitrate leaching. So it's not just irrigation, but also the precipitation. And the second reason is the soils. Though both sites have similar soils, coarse textured soils, there are some subtle differences between the soils. At Westport, we have high organic matter, so high soil water holding capacity soils at very shallow depths, and then all gravel below 22 inches of soil. So that could be one reason of heavy leaching at Westport than at Becker. Have you considered remote sensing of soils, soil temperature and brightness to better define static management zones? For not yet, but we are looking into different ways how we can use remote sensing data for in-season management of both of our components, water and nitrogen. So that's ongoing right now. So, but we haven't looked at into soil temperature and brightness yet. Yes.
Have you thought of plotting your nitrogen leaching against total water input instead of precipitation or irrigation amounts? You're actually looking at total water.
Yes, no, that's something that we would do. This is the 2 years of data that I showed. Oh, so do we have plans of plotting our nitrate leaching data and looking at the trends of nitrate leaching with total water, so precipitation and irrigation? Yes. So I haven't showed you that data, but yes, we have all that data that we can do that.
I have a question for you. It looks like you had almost crop failure some years under the rain fed.
Yes.
But yet we don't see real high nitrogen losses. Why don't we see high residual soil nitrates in those?
So I showed so we also took the plant samples even in the rain-fed plots, and we did see very high nitrate, even higher than our irrigated treatments in rain-fed plots in just the green part of the plant. So grain has the lowest, like significantly lower nitrogen uptake, but all that nitrogen that we put in the rain-fed plots was extracted by the plant, but not by the grain because there was no grain.
So the carryover was still fairly low.
Yes, the carryover is still very low. I didn't show the soil test data. We also do soil testing at 12 inches and 24 inches after harvest, how much nitrate is left over in each of the treatment. And we did see a little bit higher concentration of nitrogen under rain fed than others.
Any other questions? Thank you, Professor.
Thank you.